Okay, grade 12 chemistry. This is a quick video about VSEPR, which is the valence shell electron pair repulsion theory. It's a theory that helps us predict molecule shapes. Molecule shapes. Here's what we're going to be talking about today. First, we're going to talk about the 6 or 5 basic VSEPR shapes. Lots of people say VSEPR, so I'll probably just say VSEPR. Then we'll talk about the effect of lone pairs on these shapes, and then a little bit about real molecules versus the model. So it should be a pretty quick video. This is a really good companion to the intramolecular forces video. As you can imagine, the shape of a molecule will help us predict what kind of forces it's going to have. So the first thing is, let's talk about VSEPR or VSEPR itself and what it stands for. VSEPR stands for, or VSEPR, V-S-E-P-R, stands for valence shell electron pair repulsion. Valence shell electron pair repulsion. Interesting fact about VSEPR or VSEPR, it was created by Ronald Gillespie, or Gillespie. He's a researcher at UBC. He's still there. He's still actually actively working on molecular shapes. I believe he's like 94 years old now, but he's still researching chemistry, which I think is really cool. So it's Canadian theory for shapes. And as you can imagine, repulsion is a big part of this model, and that's why to keep in mind up here is that electron domains are negative and they will repel each other. The other piece is electron pairs, so those lone pairs are going to be important. So what do I mean by a domain? This is the first thing that I want to talk about, is a domain. Domains. VSEPR identifies different domains. A single bond is a domain. It's one domain. A double bond is also just one domain. So is a triple bond. Right? Each one of these is its own domain under VSEPR, and also a lone pair. Basically, you can think of domains as a region where electrons are going to be. So a double bond, even though there's 4 electrons there, only counts as one domain under VSEPR, because when the double bond moves, all 4 electrons are going to move together rather than moving individually. Same thing with triple bonds, and same things with lone pairs. Lone pairs are thought of as these little clouds of electrons in VSEPR. So that's the first part. The second part is the repulsion aspect, that they will repel each other. And so the basic VSEPR shapes, are based on how far apart, what is the maximum distance that we can get the domains apart. So we're going to skip over one domain because there's only one way to arrange 2 atoms, that's a line. But if we have 2 domains, you have a central atom. And then you'll have, if one domain is out this way, the second domain wants to be as far away as possible going that way. So you have a 180-degree bond angle, and the shape is called linear because it's a line. This is about having 2 domains, so it doesn't matter if it's double bonds, single bonds, triple bonds. You can have something like beryllium chloride, which is single bonds with 2 domains. You can have something like carbon dioxide, which is still 2 domains because those double bonds stay together, but that's a linear molecule. And you can even have things like this, which is acetylene, and you have 2 domains around your carbon, and it's all linear. It's a linear molecule. Triple bonded carbons tend to be linear. So that's 2 domains, that's called linear. 3 domains, to spread 3 things around as far as we can. You have your central atom, and think about it, how would we split 3 domains Well, if we have one like this, they will spread out as much as possible. You'll end up with kind of an equilateral triangle setup going on. Now the bond angle here would be 360 divided by 3, so that's 120 degrees between each one. This has a name. This is called trigonal for obvious reasons because it's the triangle. Trigonal meaning 3 sides. Trigonal, and because it's flat, it's called trigonal planar. Trigonal planar. So this is very, very flat. The 3 of them will make, because what they spread out as far as they can, it'll be very, very flat. It's a very flat molecule. So that's trigonal planar. So those two are flat. There are various examples of trigonal planar molecules. A good example of this might be something like this, formaldehyde, 3 molecules, planar. Or if you remember in chemistry or in biology, you might have something that's like a carboxylic acid. The carboxylic acid part has a trigonal planar shape because there's 1, 2, 3 domains. 3 domains. So that's trigonal planar. So that's 2 and 3. Those are the first 2 shapes, linear and trigonal planar. For the fourth, though, for 4 domains, things get interesting. 4 domains. Right? A very common mistake that I see people make is they think that 4 domains is going to follow the same pattern where we spread it around in a circle. This is not true. This is not what 4 domains looks like because you have to remember that this is in 3D. It's in 3D. So 4 domains actually adopts what we call a tetrahedron. A tetrahedron. A tetrahedral arrangement. And it's basically, there's 1 sticking up, 1 here, 1 here, and 1 here. It looks like, if you kind of know your history, in World War II, they put those things on the beaches to stop the tanks from coming up. That kind of thing. It's a tetrahedron. I'll show you it on the model here. Let's click the model. We'll add 2 bonds. So here's a trigonal planar. You see that plane? It's very flat. I can even grab a bond, and the rest of them will move to adjust. Move to adjust. Move to adjust. And it's still flat. And I can wiggle that. But if I add, I'm going to add another bond here. Because it's in 3D, this is actually the best way to spread 4 bonds around a central atom in 3D. So that's called tetrahedral, and you can think of it as a bent and another bent. So it's kind of like this and then this, and they go together like that, and that's a tetrahedron. The bond angle is the perfect tetrahedral bond angle is 109.5 degrees. But what we have to kind of do is draw that. We have to draw a 3D shape on a 2D surface. So you've probably seen these kinds of diagrams before. And what we do is exactly what I was saying before. We have a bent and another bent, and we're going to put them together. One bent can stay in the plane, so we can draw it like this. Like this. Okay. But the other one, if we take the one that's in the plane, we put the other one like this, right? And now these two, there's one back here, going backwards, one over here coming forwards, right? One back here backwards, one forwards. And we draw those in a special way. The one that's coming towards us is drawn as a wedge. We call that a wedge bond. And the one that's going away is drawn as a dash bond. So this is showing us that these guys are in the plane. Right? Let's say it's hydrogens or something. These ones are in the plane. This one's coming towards us, that one's going away. The reason the wedge bond is coming towards us, it's kind of like drawing in perspective. Right? If you're drawing something like that, and like you're drawing in perspective, that's what the wedge is trying to do. And the dash bond is just a dash bond. One thing that's really important is to keep your wedge and your dash on the same side as on the same side. They have to be next to each other because of that whole that setup, right? They're always going to be next to each other. There's no way to make a tetrahedron where the wedge and dash are kind of like that, spreading out. So that's a bad way to draw a tetrahedron. That's tetrahedral. We're going to go to 5 and 6 domains, and it's easier to just show this on this guy here. If I add another domain, something very strange happens, and you end up with this shape. And this shape can be thought of as a triangle, a trigonal planar. If we look at it from here, it's trigonal planar with that 120-degree bond angle, and a linear together. So it's almost someone took a triangle and just stuck a line right through it. This is called trigonal bipyramidal, because if you connect the sides, you end up with kind of two pyramids, and each pyramid has a triangle base. So there's one triangular pyramid up and one triangular pyramid down. So it's called trigonal bipyramidal. There's the name right there. To draw it in 3D, there's a few ways to do it. The most common way that I've seen is something like this, where you put 3 of them in a row, like that. 3 of them in a row. And then you have one coming towards you and one going away, like that. Now, it's not very common for 5 things to, so this is 5 domains. It's not very common to have 5 domains. You can imagine that 4, that tetrahedral, is the most common because of the octet rule. But sometimes you have 5 domains, and this is called trigonal bipyramidal. Trigonal bipyramidal. So yeah, you can draw it like that, or you can turn it sideways to make it look more like this guy. Okay, then we're going to add one more, and that's the last basic VSEPR shape. There are other VSEPR shapes as well, but it's rare to get more than 6 onto a thing. So if we look at the trigonal bipyramidal, you've got 1, 2, 3, right, in a flat, and 1, 2 up top. The next one just makes 90 degrees all over. 90 degrees, 90 degrees, 90 degrees, 90 degrees, 90 degrees. And this is an interesting shape. It's called octahedral. So go back over here. 6 domains is called octahedral. 6 domains. 6 domains, it's called octahedral. Octahedral, kind of hard to draw, but you can go up, down, and then typically what I'll see is 2 wedges and 2 dashes. So you have the octahedral with the 90 degrees to show that. Octahedral meaning 8 kind of planes, 8 panes of glass kind of thing. That's octahedral. Those are the basic VSEPR shapes. That's the basic shapes. We're going to go to the effects of lone pairs. So the effects of lone pairs is the next thing that we want to talk about. So let's talk about shapes with lone pairs. Basically, if you look at the keep in mind up there, it tells you everything you need to know. Lone pairs will still repel. This is why it's called valence shell electron pair repulsion. So lone pairs still repel, but they don't stick out. They stay near the central atom. So they're going to make the basic shape. They're going to be a domain, but they're not going to contribute to the shape of the atom as the shape of the molecule as other molecules see it. This is confusing to talk about, but a lot easier to explain when we draw it on a whiteboard. Let's make a 3-domain molecule. There's 3 domains. It'll start with trigonal planar, so 3 domains. Right. But I'm going to replace one of my domains with a lone pair of electrons, like that. So these electrons are still pushing down on the bonds. So it's still kind of, it's kind of like a trigonal planar, but the shape, they don't contribute to the actual shape. They don't stick out. So so we have a different shape now. It's 3 domains, but 1 lone pair. And this has a name. It's called bent, because chemists aren't very creative. Bent, or if you want to be a bit fancy, you can call it angular. Angular, bent or angular. So that's a shape with a lone pair. We can see the same thing here on our prediction. There's 2, and if I add a lone pair, it'll bend them down like that. Bend them down like that. Still 120 degrees predicted bond angle. Right, so that's bent. Let's go to our tetrahedron with 4 domains. With a tetrahedron, when things look like this, with a wedge and a dash, with a wedge and a dash, right, 4 domains. When there's 1 lone pair, it'll take the place of one of these. So it's still going to push down. It's still going to push down on all of these bonds. So it's still going to make a tetrahedral kind of thing, but it's not going to stick out. So it's going to keep that kind of shape that looks like a tripod with a lone pair that's just pushing down all these bonds. So you can think of it as a trigonal planar that has been pushed down. And we call that trigonal, still trigonal, but pyramidal. Okay, so just a trigonal pyramid because it looks like a pyramid. So if we go to our simulation, we add another bond, that's what it looks like. And we still have that 109.5 degree angle. One way to think about it, like I said, is it's a trigonal planar, but when we add the lone pair, it suddenly pushes things down. So ammonia is a good example of a molecule that's trigonal pyramidal. When we have 2 lone pairs, we're going to have 2 lone pairs, right? 2 lone pairs. It's still going to be a tetrahedron electronically, but they're going to push, the lone pairs are going to push on the 2 on the 2 bonds. And there's 2 bonds, they're in this arrangement like this, 109.5 degrees. 9.5 degrees. That's back to being bent. Back to being bent. But it's more bent. That's not an official name. It's not more bent. That's not the name, but it's more bent than the other bent. It's 109 degree bent. Or angular. Again, you can say angular. Water is the classic example of this molecule, right? Water has that oxygen, 2 lone pairs, and hydrogen, hydrogen. So that's why we draw it like this. It's a bent molecule. It's a bent molecule. And that's what gives it its properties. It gives it its polarity, makes it a liquid at room temperature, and so on and so forth. So that is bent or angular. We can go to our our simulation here, take away one of these, add another lone pair, and there's your bent. Right? It's still making a tetrahedron, it's just that two of the things in the tetrahedron are lone pairs. And I can move the lone pair, and it'll adjust accordingly. So that's bent. For 5 domains, we have my favorite molecule shape. So when we have 5 domains, you recall I drew it like this. Like that. I drew it like that. If we have one lone pair, it actually has a choice of which one it will replace, because there are 2 different bond angles here. This bond angle between these two is 90 degrees, right? Between these two is 90 degrees. But this bond angle between these two is 120 degrees. And the concept for VSEPR is the electron pairs, because they're tighter into the atom, have a higher repulsion than any of the other bonds. So the electron pair is actually going to take over this spot here, because that 120 degree angle is further away. It's further away. It's not going to take one of the linear pieces, it's going to take one of the triangular pieces. That leads to this shape, that shape. And that shape is really kind of funny because it looks like this, that kind of thing, with 2 like this and 2 out here. And people thought it looked like a seesaw, so they literally called it seesaw. That's the seesaw shape. That is the official VSEPR name for that shape. We can look at it in our simulation here. Take away a lone pair, add some bonds. There we go, and you can see that seesaw shape. Right? You can imagine it'll seesaw like that. So it's a seesaw shape. If I add another lone pair, you get another very good shape, because the second one is going to take out this guy. So if I replace it with a lone pair, here you go, and you get this. You get this shape. This shape. And that shape has a funny name as well, because if we take away one of these, we take away the other one that's in the triangle, it just makes that, and if we rotate it correctly, it looks like this. We call it, with 2 lone pairs, we call it T-shape. Call it T-shape. So it's a molecule that literally looks like a T. If you have 3 lone pairs, you'll take away the last piece of the triangle. And you're going back to linear. So that's the last piece. Of 5 domains, we're going to get to 6 domains in a second. And the last one is the 6 domain. 6 domains. The base shape is called octahedral, where we have the kind of a square with two things up and down. It's octahedral. If we have one lone pair, it takes away, it doesn't matter which one it takes away, because octahedral is perfectly symmetrical, so it's going to take away this one here. One lone pair, you get a square base with one sticking out the top. We call this square pyramidal. Square pyramidal. 2 lone pairs is actually going to take the other side, because the lone pairs want to be as far away from each other as they can. They have the strongest repulsion. This is why VSEPR, electron pair repulsion. They'll go opposite sides. You'll end up with 2 lone pairs. It's just called square planar. or sometimes just square. So it's a square, it's flat, it's a flat square. 3 lone pairs, It doesn't matter which of these get taken out. We'll take this one out, say. 3 lone pairs, that one gets taken out. These are still 90-degree angles, so you end up with T-shape. And 4 lone pairs, that does actually matter. It'll be as far away from the other as it can get. And you'll end up with 4 lone pairs is called linear. We're back to linear with 6 domains and 4 lone pairs. If we go back to the molecule shapes, to this thing, we can add some more of these, take away a lone pair. So here's an octahedron with 1 lone pair. You see that square pyramid shape, so it really does look like a square pyramid. If we take away a bond and add another lone pair, and now we have that square planar. Take away a bond, add another lone pair, you get that T-shape. There's that T-shape. And take away a bond, add 1 more lone pair, you see that linear shape that develops. So that's molecule shapes. Those are the effects of lone pairs. The last piece in our learning goals is real molecules versus simulated molecules. So we'll pause. So we're talking about real molecules versus simulated molecules. Remember that these are, this is a simulation, and the ideal bond angle. So for example, if I have a tetrahedron, the bond angle is 109 degrees. If I take 2 of these away and put them for lone pairs, this model predicts the same 109.5 degrees because that's the tetrahedral bond angle. But in a real molecule, like water for example, if we actually measure the bond angle of water, we get 104.5 degrees instead of 109.5, right? The real molecule has them pushed in a little bit more. And that's where the keep in mind comes in. Lone pairs repel harder than most other bonds. So the actual bond angle in water is a little bit less than 104.5 because of the lone pair action. If we look at CO2, that's fine, 180, 2 domains, it's linear. SO2, the model predicts 120 degrees because it's trigonal planar, right? It's a plane, trigonal planar. But the real molecule is 119, so a little bit more pushed in because the lone pairs are repelling harder than most of the other bonds. If we look at XEF2, xenon difluoride, the model predicts 180 degrees. The real molecule also has 180 degrees because linear is linear. BF3, flat, 120. CLF3, the model is T-shaped. The model is T-shaped because it's 5 domains and 2 lone pairs. But the real molecule has a little bit less than 800, a little bit less than 90. It's 87.5, and even a little bit less, 87.5 compared to 90. Because, once again, those lone pairs push a little bit harder than those bonds do. Same thing happens with NH3. The ideal is 109.5 for a tetrahedral bond angle, but the lone pair, that one lone pair pushes a little bit more, makes it 107.8. Notice that that's not quite as bad as water. Water 104.5, NH3 107.8. That's because water has 2 lone pairs pushing down. NH3 has just the 1 lone pair pushing down. CH4, perfect tetrahedron. SF4 has, it should be a seesaw with 90 degrees between each one and 120 there, but the real molecule is pushed down by the lone pair, so it's less than 90. You don't have to predict it or memorize these angles, just know that it'll be less. The angles will be less than the optimal angle because of the stronger repulsion effect of the lone pair. XCF4 is fine, it's a square planar. BRF5 should be square pyramidal, like should be a perfect square pyramid, but is really a little bit of a lopsided square pyramid. Because again, the lone pair pushes a little bit harder. PCL5, a perfect trigonal bipyramidal. SF6, a perfect octahedron. So that's everything we were going to talk about today. Right? We've talked about the basic VSEPR shapes, the 6 basic shapes. We've talked about the effects of lone pairs. And then we talked about how in real molecules the lone pair effects are more important than the individual domains. So all domains are not created equal in real molecules. That's it for today. I will link this this little guy in the description down below. Yeah, thank you very much. I'll see you in class.